let's think about whether eigenvectors are linearly dependent or independent. So eigenvectors coming from a single eigenspace could be linearly dependent, depending on how many of them there are. But suppose we have eigenvectors v1 through vk coming from distinct eigenspaces. So the eigenvalues associated with those eigenvectors, lambda 1 through lambda k, are distinct eigenvalues. So these are all different eigenvalues. Are these vectors linearly dependent or independent? Well, let's suppose that we have a non-trivial linear dependence relation, say a1 v1 plus dot 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 plus a k vk equals 0. Now, at least two of these a's have to be non-zero. So to be a non-trivial linear dependence relationship, at least one of them has to be non-zero. But all of these eigenvectors, none of them are 0. Right? So if we had just a single coefficient here that was non-zero, then what this linear dependence relationship would look like was just a1 v1. If all the other coefficients were 0, we'd have a1 v1 equals 0. But if a1 isn't 0 and v1 isn't 0, then their product can't be 0. So at least two of these a's has to be non-zero. So let's suppose a1 isn't 0 and a2 isn't 0. Okay, now if it's not the first two of them that are non-zero, then just relabel everything so that the first two of them are the ones that are non-zero. Okay, what we can do now is, to think about to prove anything about the linear dependence or independence of these vectors, we are going to have to use the fact that they're eigenvectors. And to sort of get that fact into the game, we could multiply both sides of this on the left with a. I guess I should say these are eigenvectors and eigenvalues for some matrix A. So let's multiply on the left by a. What you get is, actually, before I do that, I'm going to have to be writing this a lot. So how I'm going to write this is sum from I equals 1 to k of ai vi. Okay. So now let's multiply on the left by the matrix A. Well, on the right-hand side, a times 0 is 0. On the left-hand side, matrix multiplication distributes, so we can move this a inside of our sum here, and then we can move it past the scalar. So this is sum from I equals 1 to k of little a I times capital A times vi. But these are eigenvectors, so we get sum from I equals 1 to k of little ai times lambda I times vi, and this is equal to 0. So now there are two cases. So the first case is if lambda 1 is 0. Well, if lambda 1 is 0, then the let me write this here. Case 1, lambda 1 equals 0. If lambda 1 is 0, then this sum actually doesn't have a first term, right? Because there's a scalar 0 right here. So this is actually I equals 2 to the k, or 2 to k, ai lambda I vi equals 0. Okay, so we were able to come up with a linear dependence relation with one fewer vectors, right? What I'm going to show is that that's also possible if if lambda 1 isn't 0. Okay, so case 2 is lambda 1 isn't 0. So in this case, we can take this sum from 1 to k of ai lambda I vi equal to 0. Divide both sides by lambda 1. To see how this works out, what I'm going to do is actually write out the I equals 1 terms separately. So this is A1 lambda 1 V1 plus all of the rest of them. So I from 2 to k of ai lambda I vi equals 0. Okay, so now let's divide both sides by lambda 1. We get a1 v1 plus the sum from I equals 2 to k of ai lambda I over lambda times vi equals 0. Okay, now this is equal to 0, but remember we had another way of writing 0. Our original linear dependence relationship was a1 v1 plus the sum from I equals 2 to k ai vi. Right? So these are both equal to 0, but that means they're equal to each other. So now what I'm going to do is take all this stuff on the right-hand side and subtract it from both sides. Now we have two a1 v1 terms, so those are gone. And in the remaining, so the remaining stuff is sum from k equals 2 to k ai lambda I over lambda times vi minus sum from k equals 2 to k ai times vi. And now that's all equal to 0, because when I subtract this from both sides, there's nothing left on the right-hand side. Okay, but now I can simplify this sum. So this is sum from k equals 2, sorry, I've started writing k's. These should be i's. Sum from I equals 2 to k of ai times, right, each of these has a vi term for I from 2 to k, so we can factor out the vi, and we get lambda I over lambda minus 1. Okay, now the thing is, remember all of these, oh, this should be lambda 1 right here. And there. Okay. Now the thing is, lambda I over lambda 1, right, all of the lambdas are distinct. So lambda I over lambda 1 is not 1, right, because lambda I and lambda 1 are different. And that means that lambda I over lambda 1 minus 1 is not 0. Okay? So what we have here is we have a linear combination of the v's, except for v1, right? So this is a linear combination of v2 through vk. And it's non-trivial because not all of these coefficients are 0. Right? If you look at none of these parts are 0, that's what we just showed, and at least a2 isn't 0. So this is a non-trivial linear dependence relationship. So that means v2 through vk are linearly dependent. Okay, so now let's take a step back. Whether lambda 1 was 0 or not, we got a linear dependence relationship for v2 through vk. Okay, so the conclusion we can draw from this is that we actually, in our list of vectors, we didn't need v1. So now we know that v2 through vk are linearly dependent. Okay, but look, now we can do the same argument all over again and eliminate another vector, and then another vector, and then another vector. So repeat. Right? This whole argument let us throw away one of these vectors. Well, when does this argument stop working? This argument only stops working when there's a single vector, right? But a single vector has to be linearly independent because it's non-zero. So what we assumed was that these eigenvectors were all linearly dependent. We showed that one by one we can throw away vectors and still maintain our linear dependence. But we derive a contradiction because what we find is that a single vector has to be linearly dependent. But that isn't the case. A single vector isn't linearly dependent. It's linearly independent. So we've derived a contradiction, and that means our assumption had to be false. So our original vectors, v1 through vk, have to be linearly independent. So this is sort of an interesting fact that vectors coming from different eigenspaces have to be linearly independent.